In this video, we are going to continue our journey into the world of Bluetooth Low Energy advertising. If you haven't seen the first part of this masterclass series, then I highly encourage you to watch that because it covers all the basics and the foundation for Bluetooth Low Energy advertising and focuses on the legacy advertising, which is the main advertising type that is used by all Bluetooth Low Energy devices. Now, what we're going to cover in this specific video is what's called extended advertising, periodic advertising, and periodic advertising with responses, or PAwR. These are new features that were added to Bluetooth Low Energy since the release of 5.0 back in 2016. So we are going to do what we did in the first part and cover the things at the theory and the foundational level, and then take that knowledge and apply it to the BG22 Explorer kit from Silicon Labs. In addition to that, we'll be using a Bluetooth sniffer to take a look at how things work at that packet level. So let's get started. All right, so what are we going to cover in this video? We are going to go over extended advertising, periodic advertising, and periodic advertising with responses, or what's called PAwR. Now, we will showcase a PAwR demo at the end, and you'll see that achieving longer range with large scale or potential for large scale network and communication using Bluetooth Low Energy. This is a pretty cool feature, and paired with long range mode can really do a lot and solve a lot of use cases and address a lot of scenarios and use cases and different applications that were not possible before. So I'm really excited to show you that demo. Now, throughout the extended advertising and periodic advertising parts, we are going to do some exercises, run them on the BG220 Explorer or 22 Explorer kit, as well as using a Bluetooth sniffer, the mini morph from RF Creations, and capture the sniff and sniff the packets throughout to better understand how things work at the packet level. So again, we are using this specific Bluetooth module Explorer kit from Silicon Labs, the BGM220 or BG22 Explorer kit, along with the RF Creations Mini Morph Bluetooth sniffer. So, extended advertising. I like to say that when legacy advertising is not enough, then you use extended advertising. And this is why. So, extended advertising was actually introduced back in 2016 in version 5.0. And it allows you to use the secondary advertising channels, or what were commonly used before that as the data channels. So they were only used for connections and during connections between two devices. These are now renamed to be called the general purpose channels. Now, these are channels 0 to 36. Again, if you recall from the first video in the series, we covered that the legacy advertising uses 37, 38, and 39. Well, with extended, it allows you to go beyond that. Now, it still requires that you use those legacy advertising channels in the beginning. So the primary advertising channels 37, 38, and 39 will still be used, and we'll see the mechanism behind that. But then a lot of the other data, the actual advertising data, will be sent on the remaining channels, the general purpose channels 0 to 36. So the main reasons behind introducing this was to offload the advertising data to less congested channels. The channels 37, 38, and 39 are very congested because there are a lot of Bluetooth Low Energy devices everywhere around us, and even phones and beacons, and all of these, in many cases, they actually stay in the advertising state, so they keep occupying 37, 38, and 39, these channels. So that means that it leaves little room for other devices to play nicely, and it causes some issues. So we wanted to be able to offload a lot of the advertising data to the less congested channels, the channels that are used for connections usually, and those are channels 0 to 36. So that's the main purpose, the first purpose. Also, now we can send more data than what we could send on the primary advertising in the primary advertising packets on the primary advertising channels. So as you saw before, we had a limit of 31 bytes. Now we actually have up to 254 bytes in a single packet. And we can do what's called chaining, and that allows us to send a total number of 1,650 bytes. So compare that with 31 bytes and you see the huge difference in capacity that's allowed with advertising data using extended advertising. So if we refer back to this table, which we looked at in the previous video in this series, we saw that this lists all the different advertising or PDUs that are allowed. So this doesn't differentiate between extended and legacy, but we know from the previous video, we also talked about where ADV EXT, anything that has the EXT will be extended, and the ADV EXT IND will be the one that's sent on the primary advertising channels. And then anything that starts with AUX, the auxiliary, those are the ones that get used on the secondary advertising channels or the general purpose channels. So what's special about ADV EXT IND here is that it is sent on the primary advertising channels. So it's similar to the legacy, but it does not contain any actual data, and we'll talk about that shortly. Now this specific one can actually use the 1 meg PHY or the coded PHY. So you notice compared to legacy, we didn't have coded PHY available to us. So this one allows us to actually use the coded PHY on the primary advertising channels, which makes sense because if you are using this coded PHY, which if you don't know much about coded PHY, it is a specific mode that is available within Bluetooth Low Energy. It is optional, but it is available to achieve long-range communication. So we've seen videos of this achieving miles of communication and interchange and exchange of data between Bluetooth Low Energy devices, especially line of sight. And this coded PHY allows you to do that by adding some redundancy in the data rather than actually requiring you to increase the transmit power. So again, this packet, this PDU type, does not actually contain any advertising data. And if we refer back to this table, it just tells us that which primary or which channels and which types of PDU types allow us to send and respond to a scan response, a scan request, as well as a connection request or connection indication. And where does that happen? So this here will represent what type it is. And if you recall from the first video, we talked about that the three kind of differentiators are whether the PDU type is connectable versus non-connectable, scannable versus non-scannable, and then undirected versus directed. So this just tells you which one corresponds to which. And you'll notice here that really the only type that we have in extended advertising is AUX ADV IND. So this is repeated for all the different event types. So you'll see here, for some of them, it's not even available. So you can't have a connectable and scannable undirected event using extended advertising. However, you can have a connectable undirected event. And in that case, it still uses AUX ADV IND. Even the connectable directed event still uses that, and you'll see it repeated here. And the way this works is that instead of having a specific PDU type that is assigned to each of these, there's data that's in the packet itself that indicates which one of these the packet is. So if we look at what the advertising data looks like, so this is the generic PDU or the generic format for a packet, a Bluetooth Low Energy packet. And we know from going back to, if we look at the legacy, that the payload was only 37 bytes. We had 6 bytes that went to the advertising address, and then the remaining 31 bytes are what was available to us to include actual data. In this case, it is different. We have up to 255 bytes here. And in this, you'll see that there's some payload, and the payload contains some header information. So there's what's called the extended header length. So this just tells the receiver to know what the length of this extended header is. And this can vary from 0 to 63 bytes or octets. So it's not always going to be constant and fixed. this will be able to tell the receiver how many bytes to associate with that and parse it so that it knows that the remaining bytes are available to advertising data. We have the advertising mode. This is what we just talked about. So the PDU type that was indicated in legacy advertising using the actual PDU type. In this case, the advertising mode is actually indicated via 2 bits. So whether it's connectable undirected event, which is non-scannable, or whether it's connectable directed, for example, or any of the other ones, then that will be indicated here in this advertising mode bits. So the extended header, and what's interesting here about this payload is that it's not that we have up to 64 bytes for this and then up to 254 bytes for this. In fact, the 0 to 254 means that we actually have 254 bytes for these two together. Excuse me, but the extended header does not necessarily contain all these bytes. So if the extended header was 0, for example, and I don't know if that's even possible, but I think it is, and you can have that to be 0, in that case you have up to 254 bytes allowed for the advertising data. However, if you have some bytes and you have data in the extended header, then that eats up from the space available in the advertising data. So keep that in mind. It's not similar, it's not the same as legacy where it's always 31 bytes that's available to us. In this case, we have something or the amount of bytes that are available to us in the advertising data field depends on the extended header and what that includes in it. So I won't get into the details of what the extended header has. You can refer back to the specification and take a look at that. It's a lot more, there's a lot of details in there, and not a lot of the fields get used in general, but for very simple applications, we wouldn't need to worry about it. In fact, when we use the APIs and the exercises for the Silicon Labs SDK, for example, you won't even have the option to control that. So that's being built and added by the stack itself. We just control what goes into the advertising data. So that's why I'm not going to cover that in detail in this video. So this is how this extended advertising mode works. So we have this ADVEXTIND, which again, we talked about that. That's the PDU type that gets sent on the primary advertising channels. So 37, 38, and 39. But this does not actually contain any data, any advertising data. Rather, it contains pointer information or some small amounts of information that tells the scanner where to go to find the actual advertising, the secondary advertising data and the secondary advertising packets. So these are the ones that are sent on any channel between 0 and 36 inclusive. And in this case, it will contain, for example, the timing, so that it would know, the scanner, that from the reception of this packet, for example, it's at an offset of this much. And then it will indicate the phi that's used, as well as some other information that is needed to locate this, the channel and the timing as well. So once it does that, the scanner is now able to find this. And at every advertising event, so every interval, so if we had an interval of 100 milliseconds, then every 100 milliseconds, you'll see most cases, you'll see 3 advertising packets sent on the primary, and each of them will contain pointers or information that tells the scanner where to find this packet that is sent on the secondary. So that's how it works, and this is where the data will be contained. So the scanner will need to find at least one of these in order to know where to find this packet, and then go read that packet, parse it, and read the actual data from it. Now, in terms of connections and even scan requests and scan responses, which I'm not showing in this specific diagram, but here it's the same. However, after, and this I have a typo in here, but excuse that for a moment. But once it finds this, this is where the actual connection request is allowed. So it's not allowed on the primary advertising channels, rather it's allowed only on the secondary advertising channels, the general purpose channels. So if a scanning device decides to connect, it will need to scan for these, find one of them at least, know where to find this one, which is supposed to be AUX ADV-IND, not ADV ADV-IND. That's a typo on my end. And then from there, it can send the AUX connect request and then get a connect response. And you'll notice here that there's a little bit of a difference between the legacy and the extended. In the case of legacy, we actually don't have a response, and the connection packet or the establishment, the initiation, it is not a request. It's called an indication. We can see that in here. This is a connect IND in the case of the legacy versus AUX connect request. And so there's a response that comes back, whereas in the case of legacy, the connection happens later on as the first packet that comes from the central device, and we won't cover that in detail in this video because we are focused primarily on advertising. But keep that in mind that there is a response to a connection request packet in the case of extended advertising, whereas in legacy that does not exist. And a single packet allows us to carry up to 254 bytes, again, depending on the length of the extended header. But that's in a single packet. So with extended advertising, there is a new concept called chaining. And you'll notice that there is in that table something called, or it's not in the table, but I have it listed here. It's called AUX chain IND. So that's a new type that is assigned to an extended advertising packet. And that is basically is considered a continuation of a packet. So this is what happens. It's the same as sending the extended advertising. Again, the advertiser, the scanner will need to find one of these to find the offset, to find this. But then this will actually have a length that spans more than one packet. And in that case, it will indicate to the scanner that it needs to look for more packets because the continuation, the data is not complete yet in that single packet. So that's the way that this 1650 bytes can be sent using extended advertising, is the use of these AUX chain IND packets. All right, so now let's go to Simplicity Studio and run some of these exercises. We'll focus on the extended advertising for this part of the exercise. We'll change some of the primary and secondary files, and we'll take a look at sniffer captures throughout this. All right, so here I have Simplicity Studio open, and these examples that we'll run through in this masterclass are available in the GitHub repo that I created for the first one. So I'll include a link to that below the video as well, so you can refer to it and run each of these examples. So I have the extended advertising example here, and app.c is where we really want to be looking at. Let me make this a little bit bigger and zoom in. So let's take a look at what we are doing in this application. Again, the system event, system boot ID event, is where the stack gets instantiated and we're ready to get started. All we're doing here is we're getting the Bluetooth address and printing it out, which is pretty important because I'll be using a Bluetooth sniffer to capture and look at the device and its data, and the easiest way to find the device is by the Bluetooth address. So in here, the only thing it is doing is creating an advertising set, and we will look at what that is setting up. So it's calling a function here called demo setup start extended advertising, and let's take a look at what that has. So in here, we're actually building an array of bytes that is up to 226 bytes. In addition to that, we'll include some flags and local name and stuff like that. So the first thing that we have is the flags. So the flags, if we recall, we covered this in the first part of this masterclass series, and we have a length, type, and flag data. This just says it's BR-EDR is not supported, and it's general purpose, general discoverable mode. The second thing I have is a local name. I'm calling it coded phi in this case. And then after that, I have the manufacturer specific data. So we have 3 elements, basically advertising data elements inside the advertising data field. So in here, I just go and randomly assign the values going sequentially from 0 up to this 226. And then all I'm doing there is setting the extended advertising data with the bytes and the data, and then we start it. So this will get called after. Let's double check. So this start is what actually calls the build or the setup. So this setup is called, and this is the function we just went over. And here we're advertising at 100 milliseconds. So this, but you can see the APIs all include extended advertiser. So that's the main difference. Here I'm using coded phi for both. I could change that and have it so that it uses 1 meg phi for so these 2 parameters define one for the primary advertising channels, and the other one is what's used on the secondary. So you can have those separately. You can't have the 2 meg phi on the primary. On the secondary, you can have either 1, 2, or the coded phi. So let's start with the coded phi on both, and we can see that, and then we can change one of them and see that reflected on the sniffer as well. So I'm going to go ahead and build this. And I had already built it. I have my device connected. I'm going to connect the Bluetooth sniffer. So let's flash this to the device, and okay, so that all looks good. I have the Bluetooth address now. So let's take a look at that in the Bluetooth sniffer software. So here's the Bluetooth sniffer software. I just connected the device, so need to connect to it, the hardware, start the scan, and disable all these other protocols. I'm going to disable advertising. Right now I have a device filter, so I need to go to here. Let's disable Zigbee as well, 802.15.4. So paste in the address and then select it, and now I have the actual data. So you can see here, we have advertising chunks. So this is grouped. I can go to logical. That will show me a lot more detail and in a more flat structure what is going on. So that will help us see it much better. I will keep this area open because we want to look at the details, but you can see here, so going back to, you'll see that we're expecting to see 3 primary advertising packets, and then finally an auxiliary packet, and then back and forth. So it will go back to advertising 3 and then 1, 3 and then 1. And that's what you'll see here. So you see here ADV-EXT IND, 3 of them, and then an AUX ADV IND. 3 of them, AUX ADV IND. So what is in each of these? So let's take a look. These are the 3 that are sent on the primary channels, and this is the index of the channel, not per the Bluetooth SIG or the SIG, but I can include the channel index. So let me see how to do that. Yeah, so this tells us, so I can see here the channel index, and you can see here 37, 39, 38, and then 22, 37, 39, 38, and then for some reason went to 36, 37, 38, 39. So the sequence can change, but then from these packets you'll be able to tell where the scanner will be able to tell where this auxiliary packet is located. So let's take a look at that. So here's this one, for example. Let's take a look at the contents of that. you can see here there's something called the auxiliary pointer payload. So it tells us that the channel is 22, and that's confirmed here. It gives us some clock accuracy, so it knows to add some margin of error to the offset of the clock. The offset units are 30 microseconds, and then we have 183 of them. So if I multiply 183 times 30, that will give me 5,490 microseconds. And it's also saying that the phi is the coded phi, which is what we expected. So let me see if I can do this and look at the timing. Let's move the delta over. Okay, so we have the delta here. So from here, we're expecting 5,490 or so, and that's what we see here. So there's a little bit of margin error, that's expected because of the clock accuracy, and so this is not as accurate as something like periodic advertising. So you can see here it's 5,496 microseconds or 5.496 milliseconds. But what's interesting is, each of these is going to have a different timing offset, but the remaining parameters will be the same. So if you look at this one, it'll still say channel index 22 on the second one. You just see that the offset changed from 183 units to 125 and then down to 67. So this gets updated. So if a scanner finds either of these, it'll be able to use that information to find the actual auxiliary packet. And in the auxiliary packet, let's take a look at what's in there. We are expecting 3 types of advertising data payloads. The first one is, and here you can actually see what the extended header includes as well. So that's another interesting thing to see, because we don't have control over that from the application, and that is defined by the stack itself. But here we can see what's included. I won't go through all of that. I will skip and look at the actual data. So we're going to look at the advertising data. It looks like it's 245 bytes. If you add that to 9 bytes, you have 254, which is the maximum that we talked about. And then we have the length plus the advertising mode all equal 1 byte, and so together it'll be 255 bytes. So the first thing we have is the flags, and it's 020106. If we look at that, what does that mean? 02 is the length, the type, and then we have the general discoverable bit set and the BR/EDR not supported bit set as well. Second thing is going to be the local name. We have it set as coded phi. And then finally, we have the actual manufacturer-specific data, which I have defined using the novel bits company ID, and then everything is just sequential going from 00 all the way to E1, which is 226, it should be. So that's the random or the sequential data that I'm including. And you can see here I'm not changing anything. Going from one interval to the other or over time. So you'll see that this gets repeated over and over again for each time. And you can see it's pretty consistent here that you have 3 and 1, 3 and 1, 3 and 1. Okay, so let's go and change the phi just on one of them. So I'm going to change it to use the 1 meg phi on the primary. Go ahead and build. That built just fine. I'm going to flash it. Make sure that things look good. Yep. Okay, so now I can go to the sniffer. I'm going to start a new capture. I don't need to save this. And in here now, if I look at each of these, I should see that this is being sent on the 1 meg phi. Yep, and that's confirmed right here. So we have 1 meg-PHY for modulation, and then the auxiliary is still being sent on the coded PHY, and in this case it's the S equals 8, which corresponds to 125K. So that's what they're naming it here instead of saying just coded, because there are two coded configurations. There's 125K and 500K. But you can see consistently that the first three are being sent on the 1 meg-PHY, and then the other one, the auxiliary one, is sent on the coded PHY. All right, let's talk about periodic advertising. So I wanted to start with a simple example, a hypothetical example. So let's say we have a number of temperature sensors that are distributed in a building, and we have those sensors sending out temperature readings and information, and this information and these temperature readings are changing over time. And this data needs to be distributed to multiple devices. So imagine that we have different kind of readers that are distributed throughout the space, and they all need to read from all the temperature sensors and so on. So how do we solve something like this? We could use extended advertising. We would have to use advertising, obviously, because it's much more scalable, and in order to be able to have multiple devices be able to receive the data from the other devices. So broadcasting and advertising makes the most sense in this use case. And we could choose to use extended advertising. But that does mean that the central, if you recall, that the central would have to be scanning for the advertising data or the advertising packets, especially the primary ones, all the time, because it can't find the next advertising event's auxiliary packet unless it goes and scans for the primary. So you could have a use case where the readers or the scanner devices are actually battery operated, and they need to be sensitive about power consumption and current draw, and they need to last longer on their batteries. Also, in the case of extended advertising, if you do by chance miss any or all of the packets on the primary channel, then you actually miss you won't be able to find the packet that's sent on the auxiliary packet sent on the secondary channels. So instead, the working groups came up with what's called periodic advertising. So this actually allows multiple devices, scanners, to synchronize to multiple one or more peripherals. So the peripherals will now instead, and if I go back to my example, you can see here that even if we were to rely on advertising, extended advertising, then you can see here that the scanner does not know exactly when a packet is sent on each of the channels, because there is a kind of a random offset, random delay between the packets that are sent on the different channels. In the case of periodic advertising, however, this actually allows you to send, or allows the advertising device to send at specific exact times periodically. So it allows the central device to know exactly when the advertising device is going to send that advertising packet, and on which channel and at which time, and so on and so forth, and using which PHY. So it allows it to be synchronized. So even the scanner devices are now able to wake up, and only wake up when they know that the other device is about to send data. And when we run the example on the Explorer board and we run the Bluetooth sniffer, we'll see that that timing is very precise compared to regular advertising. So it does help the scanner devices reduce power consumption. It could also lead to the peripheral device to reduce its power consumption. However, keep in mind that even if it is using periodic advertising, it will still use the extended advertising, because it doesn't know when a device or a scanner device came into range, or was a new device was added to this network. So it still needs to at least let the device or let any new device be able to tell where the synchronized data is. And in order to do that, it actually has to go through the same sequence that we looked at when using extended advertising, the regular one. So if we look at that, you'll see here that it is still sending the 3 packets on the primary. These point to the secondary, the auxiliary packet, but then the auxiliary actually contains information that points it to the ADV sync IND. So these, I believe it should be AUX sync IND. Yeah, AUX sync. So I have a typo here as well. But in any case, this is AUX sync IND, and these are the actual periodic advertising packets. So these will continue on. Normally, they will continue on forever, and they will have the data that is changing will be reflected in each of the packets at this time that it was, actually taking place in terms of whether that's a sensor reading or some other information that's being sent. So that's how it works. The next time, if a device goes through this sequence, finds this, it will then not need to go back to scanning for these. So it will just continue to wake up at an exact time, the periodic advertising interval, and be able to find these packets and read them and read the data that comes in it. If a new device comes in, then it will have to go through that sequence at least once in order to find these. So for periodic advertising, let's run through an example that I have prepared. Again, I'm going back to Simplicity Studio, and this application it's available in the GitHub repo, so you can download it and run it yourself locally on your machine. Once you have one of the Silicon Labs boards, again, the BG22 Explorer board or kit is the one that's used specifically for this, so the application will be configured for that. So if you use a different board, a different hardware, you'll have to update the project to use that. So I'm here, I have the periodic advertising example. Let's go ahead and look at what is involved in this. So the first thing I'm going to take a look at is go to BT on event in app.c, and again, I just have a couple of printouts here. I have a printout for the example just starting, the printout of the Bluetooth address, and then from there on I have a creation of an advertising set, setting the TX PAwR, and then setting the interval to 100 milliseconds. Everything here so far is just normal. From here now, I'm actually generating some data. So for the extended advertising, which if you go back and look at this, again, there's an extended advertising data that gets sent here, but that we don't really care about that. So we're letting the stack handle that. What we care about is looking at the sync info, and that's going to be handled by the stack as well. And that's the information that tells the scanner where to go and find the actual periodic advertising packets. Now, what we're going to include in the advertising in the actual periodic advertising packets is what we are customizing in this case. So in here, I'm just starting an extended advertising. So again, this is separate from the periodic. And then I start a periodic advertising as well. This is also being set at 100, I believe, 200 milliseconds in this case. So I think these, let's see, the default value is 200. Yep, and the time range, okay, so it's in units of 1.25. That's why the 160 translates to 200. So 160 times 1.25 will equal 200 milliseconds. So that's the default. So this is the actual periodic advertising interval. It's going to be 200 milliseconds. So in there, that's where I have some data, and all I'm doing here is actually filling it out with sequential data going from 0 all the way to 253 minus 4, because that's the maximum I can include in that. And that's where I'm using the manufacturer specific. So we have the length, we have a type, we have company ID, and then we have the actual data. I'm using the Novel Bits company ID 08D3. Again, that needs to be in little endian format when it goes into this packet. So from there on, I am just filling it out with data from 0 to manufacturer specific data length, so 253 minus 4, and going up to 253 minus 5. The other thing here is that we're actually updating this. So the first time we're doing that, but then every signal refresh data, let's see how often this happens. So the sleep timer, okay, it's 1 second. So what I'm doing here is kind of emulating what would happen in the real world with data that's changing. So we actually won't see this except for the first time, this sequential data. And then from there on, every 1 second, so every 4 or 5 periodic advertising intervals, we'll see that the manufacturer specific data will get updated to some random number and be included in the data. So that's what we're using, this sleep periodic timer, sleep timer, in order to wake up and send a signal to refresh the data. So let's take a look at what that looks like when we run it on our board. Want to make sure it runs and builds correctly, and then flash it to the device and take a look at the serial output, and that looks good. I see periodic advertising example, same Bluetooth address, so I don't need to do anything here. I'm just going to refresh and reset the board so I can see the very first part of it. If we take a look again, we'll see that there's advertising extension IND. So again, ADV EXT IND, we'll see 3 of those, AUX ADV IND, and then that will point to the AUX sync IND. So in here, we won't see that included in this part. We will see it included in the, let's go to logical. This will make it much easier to see that. So we have ADV EXT IND pointing to AUX ADV IND, and then we have the AUX sync IND. So this will contain just the offset, the auxiliary pointer payload, and the offset that we looked at, just like any regular extended and advertising. But then inside the actual auxiliary packet, you'll see that now there's a field called the sync info. And that's what gives us the information, gives the scanner the information on how to locate this AUX sync IND. So there's a bunch of things here. There's offset units, offset adjust. There's the interval, and that's the one that's defined as 200 milliseconds, just like we saw in the API. We have a channel map because this one actually uses the channel selection algorithm. And so what this means is that every packet will be known to the scanner, and based on an algorithm, it'll know exactly which channel will be used, rather than extended relying on the information being in the packets indicating which channel. From there on, it doesn't need to do that for the synchronized, for the periodic advertising, and instead it can just know from the algorithm and plugging in some information what channel it will be on. So for that, there's a couple of things needed. There's the access address that's needed. There's also what's called the event counter. These all go into they plug into the channel selection algorithm. And in this case, it's channel selection algorithm number 2 that's being used for determining which channel this happens on. After that, once the scanner finds that information, it should be able to locate the AUX sync INDs. And if you look at that, the sync packet offset is 21.54, and that's what you see here. So 21.54 milliseconds from this packet is when we should see the periodic advertising packet. And that's what we see here, the AUX sync IND. It's 21.541 milliseconds. And so in here, now you can see the actual data, which is the advertising data that we included. So This one we will have to figure out when we reset the device, because this is not the first time that this was sent. So it did update it to include the information, or the data, the bytes are updated now to be random rather than the sequential. Actually, if I look for other ones, I think I reset the board at some point, so maybe that's where we reset it and went back to random. Yeah, so here, so at some point here I reset the board, and that's when it went back to the default of just sequential data. Again, every 200 milliseconds almost exactly we will see an AUX sync IND, and you can see that here. So you can see from 0, this reference point, 200.001 milliseconds, and then if I click that, I can see that the next one is 200.002 milliseconds. So it's very, very close to 200 milliseconds. And so that's what allows the scanner to actually not have to look for any advertising packets and be able to find these packets just by knowing the exact timing of the periodic advertising interval. So if we look at that now, a few packets later, we should see that the data is now randomized. So here it was randomized, the previous one was not. So that's when the sleep timer that we looked at, the 1 second timer, got updated or was expired and caused the data to be updated and reflected in the random data in the advertising data array. Okay, so this is really how it works for periodic advertising. And so it's pretty simple. Again, we just see 3 primary advertising packets that point to the secondary, and then the secondary contains the sync information. So once the scanner will find this information, it'll just be able to wake up every 200 milliseconds to receive the periodic advertising data, instead of having to look for these packets every time to find where this is. It just needs to find this once, and then hopefully nothing changes from the advertiser side, and so it'll be able to find these packets regularly from there on and be able to conserve more power and only wake up when needed. So now that we understand what periodic advertising is and how it works, and periodic advertising as well as extended advertising was added in version 5.0. So it was back in 2016, so it's been a while since that feature was released. However, last year, or if you're watching this video later, regardless, in January of 2023, version 5.4 was released, and that included a new type of advertising, or a new type of really topology, because this will, as you'll see, it allows us to do a lot more, and something that we weren't able to do with Bluetooth Low Energy before, at least in a standard way. So this introduces bidirectional communication using advertising. So imagine now advertising devices are still able to broadcast their data, but now they actually give a chance, or they're able to receive responses from the scanners. So it really breaks the paradigm that we are used to as well, because you'll see it becomes more important or more popular and more common for the scanners to be the battery powered devices, whereas the advertisers are more mains powered or live powered devices. So this is very suitable for centralized and synchronized applications. So think of an application that has one central node, and it's communicating with tens or hundreds or even thousands, and up to 10,000, if not more, of devices. And it's able to basically group some of these. So this all happens during the provisioning or the commissioning of the network and the deployment, the implementation. So it varies across the different use cases, but you can basically group specific devices within those thousands of nodes and have them receive specific types of data or a specific type of packet, and then that packet will, these devices could act based on the information that's included in that packet and act at the same time. So it gives you the power to create synchronized behavior for groups of devices, or even just all thousands of nodes together. So it is very optimized for low power applications, but again, it kind of shifts the paradigm and flips it on its side, on its head, in terms of the device, the nature of the device that's advertising and the one that's scanning. So in this case, most of the use cases that will use PAwR will actually leverage or have the battery powered device be the one that does the scanning, whereas the live or mains powered device, the one with the bigger battery, will be the one that will be advertising. There was a new feature that was added along with PAwR in 5.4. We won't cover it in this video, but it's called encrypted advertising data. So it allows you to actually encrypt the data in the advertising packets and be able to decrypt it in a standardized way that is defined in the spec. So let's take a look at what PAwR looks like at the packet level. So it does use periodic advertising, but it goes further by taking a periodic advertising interval and segmenting it into sub-events and what's called response slots within that. So let's take a look at that. So we have an interval, and if you go back to the example that we looked at previously in the previous section, you will have just one packet being sent at every interval. In this case, we're actually taking this interval and we're splitting it into multiple what's called sub-events now. And we can have up to 128 or 255 sub-events, I believe, or 128. We'll look at that in the next slide. But we have a number of sub-events, and then within each sub-event, this is where it gets kind of interesting. We have the advertising device, sending only one packet. And then after a specific period of time, there are going to be what's called response packets. So the system will be defined in a way such that we have a number of slots, response slots, that are defined. And these are assigned during commissioning, during provisioning, the configuration of the system, of the deployment, of the installation. Different devices will be each assigned a specific response slot. So this allows the payload could talk or could be targeted towards a specific device, and then that device will respond with a specific behavior or specific action or some kind of data. But the most important thing here is that each response slot is assigned to a specific device. That's how these devices are able to respond and not step on each other's packets and the data that's going back to the advertising device. So you could have devices receiving a number of sub-events. They could receive only one sub-event. So if this is where you can actually take things further by grouping devices together. So say I have, and this is primarily was introduced for the application of electronic shelf labels or ESLs. So in that use case, if you have an aisle that has some products on it, and maybe you have one part of that aisle, the shelf, that all has the same exact product, you would have tags maybe on multiple levels and maybe going right and left where it spans all that product, the same product. And in that case, we'll probably configure it so that all these products, all these tags that represent the same exact product be part or be subscribed basically to a sub-event. So in that case, if you send a price update, you can send a price update and it will be received by all of these at the same exact time. and they will be able to each respond within their slots if they need to. But at least you can at least have them receive the data all at the same time, because they will be scanning based on our configuration. They will be scanning for a specific sub-event, and then based on that, it will receive a specific packet and be able to take action based on that. Now, obviously, this does not really work for high bandwidth and sending large amounts of data. For that case, you can actually have the device accept a connection through, I believe it's through a response slot. So you can have a device, the scanner. In this case, this will probably be the central device, or acting as a central when it establishes a connection. So if, say, for example, these tags, these electronic shelf label tags, need to update their images. And a lot of cases now, these tags actually have images on them, and they come in colored and all that, and they have bigger displays. So in that case, you wouldn't want to send the image data over the periodic advertising train. So instead, this scanner, this access point, is usually what it would be able to connect to each of these devices directly without having to scan for this device advertising and all that. It leverages the PAwR system in order to establish a connection, be able to transfer some data to it, and then disconnect and go back to the PAwR kind of work, the way that works with the advertising and the responses. The most important thing about PAwR is that it's really all about the definition and the design of the timing. Because if you think about it, we have a specific packets that need to be sent, and depending on the payload, the type, or the size of the packet, that will dictate the time that it takes to transmit that packet. So we have to make sure that the timing is defined and designed in a way that allows for the packet to be sent over the air without that time expiring. Or, for example, if we know that the packet here, T0, actually takes an amount of time to be transmitted over the air because its typical size is going to be X, then we need to have the slot delay be larger than that. Same thing for here, the responses, we need to have the spacing be larger than the time that's required to transmit each of these responses across the different devices, because this spacing is uniform between all these responses, and it doesn't matter. You can't define a specific space between response 0 and response 1, and so on and so forth. Same thing for sub-events. So if you take all this into account and you calculate that, you'll figure out how much time is needed for each sub-event. And the sub-event interval is uniform and it's consistent across all the sub-events. So you need to make sure that you know what is the longest time that any of the sub-events will take, and then use that to be the timing or the interval, the sub-event interval, and define that way. So I won't go through all these parameters, but here you can see how long, or the different timing that's allowed, or the different values that are allowed, the ranges for each of these. So most importantly, we can see the sub-events. There's 128 sub-events that can be defined. Number of response slots are 0 to 255. So if we wanted to theoretically assign each and every single device a specific sub-event, or we have multiples that have, so if we wanted to have separate devices assigned per sub-event, then we can have a maximum of only 128, because that's the number of sub-events. But if we do group things together, and then still be able to have groups assigned to sub-event and a group assigned to sub-event number 1, and if we need responses from those groups, those devices within those groups, then we can assign each device a response slot, which means that in total we can have 128 times 255 devices. So I don't know what that would look like. I forget if it's like 32,000 devices theoretically. So 128 times 255. So yeah, that's 32,640 devices, but that's very theoretical. In practice, not all these packets will be received on the first time, on the first go by the scanner devices. And there's RF congestion and noise, and a lot of there could be some retransmissions built in to the system in the implementation. So keep that in mind. So again, this specific feature was introduced to support what's called the Electronic Shelf Label Standard, or ESL, and this is published as a separate profile on top of Bluetooth Low Energy. But I don't think that's the only space or the only use case that it can be applied to. Now, that is the standard way, or that's the standard that kind of encouraged the development of this new feature. But I think it applies in a lot of other cases, such as smart home devices, asset tracking, healthcare monitoring systems, industrial automation, smart agriculture, crowd monitoring. You can define it so that it requires responses from devices that are worn by people, and then have those be an indication of whether they're around us or not, and stuff like that, sending out broadcasts of emergency messages and so on and so forth. So there's a lot more, I think, that can be solved with PAwR. Previously, before the introduction of this, a lot of people, if they really wanted to use Bluetooth Low Energy to solve a problem that was more mesh-like, that was kind of like what we are talking about here. So say, for example, ESL, they would try to solve that with Bluetooth Mesh. Unfortunately, Bluetooth Mesh is not power friendly at all. So current consumption, and the way that Bluetooth Mesh works, by the radio being on all the time to listen and to send, especially in the case of relays, it is not very practical, and it's not really suitable for this kind of application. The final thing I wanted to talk about before leaving you with a recording of a demo that I ran with PAwR is that the nice thing is that this can be paired with Coded Phi. And if you don't know about Coded Phi, don't worry about it. It's just it's a standard or a method to be able to increase the range of Bluetooth Low Energy communication. And that can be used in both advertising and connections. So it can actually work in tandem with PAwR. And in that case, you can imagine similar to like an ESL use case, but you can imagine that it can have a much broader reach and a much larger range. So I'll finally leave you with this demo, and take a look at this demo of PAwR plus long range mode Coded Phi, and I hope you enjoy it. All right, so this is the setup. I've got 4 Thunderbolt BG22s, and these are the ones that are scanning for the periodic advertising and sending the responses to this board, which is sending out the periodic advertising. And for this one, I'm going to go as far as I can across the field. I think I'll get to the end. I don't have any more space to do the test, but I'm going to see if I can still get a response from the boards by turning on the LED. So sending a command to turn on the LED. As you can see, the LED turns on and I get a response that gets displayed on the LCD here. I can turn it off. So I have 2 buttons. Button 0 turns on LED 1 with a short press, and then a long press will turn on LED 3. Button 1 will turn on LED 2, and with a long press it'll turn on LED 4. So let's see how far we can get, and we'll then measure the distance going back to the home base. So I'd say I'm about a quarter of the way, and if I look in here I can see the RSSI, and we can turn on LED 1. You can see it turn it on, and we get the response. Turning it off gets the response as well. So let's keep going. Probably about halfway or a little bit further. As you can see, the
RSSI is still at minus 80 or so, so it's still pretty strong and enough for us to get responses. As you can see, turning on the LED and turning it off. And let's keep going. Okay, this is as far as I can get, unfortunately, and as you can see here, we're still getting a good signal. So we're getting responses with at minus 80, minus 90, minus 100 dBm, and if we try to turn on the LED, we can see it still turns on and we get a response confirming that. We can also turn on other LEDs like LED 3, turn it back off. And so this is as far as I can get. You can see it's all the way back there. So now I'm just going to measure the distance from here all the way back. And if this is the test with coded phi and periodic advertising with responses. All right, so distance is around 1162 meters of 62 feet. And I'm back at the home base. So that's around 360 meters or so. So pretty good distance. We couldn't get farther than that on the field, but this is how far we can get. But we were able to cover a good distance with coded phi.
Well, if you stuck around this whole time for this video, then I'm truly grateful. I hope you liked this video and enjoyed it and found it very useful. If so, please like and share and subscribe to the channel and hit the notification bell to be notified when new videos come out covering other Bluetooth Low Energy topics. Thank you, and I'll see you in the next one.